Good evening, everyone. Welcome to the third session of the South Dakota Vegetable Short Course. I'm Rhoda Burrows, SDSU Extension Horticulture Specialist. I work with fruit and vegetable growers across the state, and I'm sitting out here in Rapid City. So I hope all of you have enjoyed the warm weather, at least that we've had in South Dakota today. I want to acknowledge before we get started that this year's South Dakota Virtual Vegetable Short Course is made possible in funding with funding from the USDA NEFA Organic Transitions Program and the North Central Region SARE Professional Development Grants. Each of these of the 4 sessions will be available on the SDSU Extension YouTube channel to rewatch and share with others, and we'll put that link in the chat box. It's my pleasure tonight to introduce Shannon Mutschelknaus from Brookings, South Dakota. Shannon is a mechanical engineer with 20-some years of experience doing thermal design, research, and testing of large electronics megasystems. He owns and operates Wayward Springs near Brookings, South Dakota, where his family raises Scottish Highland beef, Jacob sheep, exotic fruit trees, and I think he'll tell us about some of those, super hot peppers, and 2 children. Shannon has designed greenhouse heat storage systems for hobby, professional, and educational growers in many parts of the U.S. And the world, for that matter, enabling them to minimize and eliminate energy-intensive heating systems. So I'm eager to hear what he's going to share with us tonight. He's also obsessed with growing unique produce for our region and expanding the types of fresh foods that we can grow cost effectively in our climate. So tonight, Shannon will focus on findings from the 23-24 winter and growing season in his custom designed solar high tunnel. And we'll drop in the chat box. You can learn more about Shannon and Wayward Springs LLC at waywardspringsllc.com. Shannon, take it away.
All right. I will go ahead and share my screen here.
And you'll see a poll that people can respond to, and we'll show the results of that in a minute.
All right. Thanks for the introduction, Rhoda. Can you see my screens? Everything look good?
Looks good.
All right. Yeah, so tonight I'm going to talk about a project to engineer a better high tunnel. This has been a several-year-long project. Rhoda already gave a pretty good introduction about myself. So this is a little bit of just a recap with some pictures, I guess. One of the tropical fruit that I grow in my greenhouse, which was a previous project, is passion fruit. Not something commonly available locally grown in South Dakota, but we also have lots of hot peppers that go to several different local hot sauce companies that you can get. And we have Scottish Highland cattle and Jacob sheep. And we'll go ahead and talk a little bit about our outline for tonight. Seems a little slow to go to the next slide. There we go. All right. So we're going to be talking about a particular grant project, increasing the economic viability of year-round high tunnel production in South Dakota's climate. This was made possible in part by funding from USDA through South Dakota Specialty Crop Block Grant Program. Tonight, we're going to do a little bit of a review on some benchmarking of existing traditional high tunnel performance to kind of compare some potential design improvements to. We're going to look at a whole bunch of aspects of a better high tunnel. We'll talk about improving the frame geometry to improve season extension, talk about a way to insulate the north side of the structure where light isn't coming through the glazing, how to set up an efficient roll-up vent and kind of evaluate whether or not that makes sense. We'll talk about using concrete as a heat storage method. And then at the end, we'll review how the system did in its first winter and summer using just the concrete heat storage system. So first, we'll start off talking through some traditional high tunnel performance. We have a benchmark system that's located nearby. This is about 5 miles from my test site. So that was convenient. So the weather and climate are pretty similar. And so that makes it a good test site. It's also located within 1.5 miles of the Brookings Mesonet site, which gives us great weather data. It had new inflated double polyethylene film, which is typical for our climate in South Dakota. Usually people do a 2-layer and inflated film to get maximum season extension and for wind durability. It's fan ventilated. It doesn't have roll-up sides, and you can see here these are the exhaust vents. The intake is actually over here on the east side of it. It's capable of natural gas heat, but for this season the heat was not used, and it has an east-west orientation, not a north-south, east-west. So that means it's better at capturing sunlight in the winter time, and you'll see that in the temperature data when you go through that. It's also got a nice site selection where it has good full summer and winter sun exposure without trees or other buildings blocking it. It's a 34 by 96, which is a pretty common high tunnel size, and just the slopes and stuff are there on that screen. So what does it kind of look like? This grower is typically growing tomatoes. This particular picture is from late in the season. I think it's probably a November photograph after stuff had frozen in here. It's set up with traditional east-west rows along the long length of the high tunnel. The cooling fans and the vents are on thermostat. So right here, we're looking out to the west where the vents are. You can't see the vents. And then behind you is the fans. The fans come on with the thermostat, and then there's louvers that automatically open up on the exhaust for that to vent out. And typically, the tomato vines during the growing season will be up to 8 foot tall using the lower and lean method, which is the most common commercial method you'll see for that. So for the benchmarking, we're just measuring air temperatures within the structure. We set up 3 temperature sensors kind of equally throughout the center of the structure here. They're about 4 foot above ground. So usually you'll see temperatures below that will be a little bit warmer, and temperatures above that would be a little bit colder at night. 4 foot is what I use for most of the benchmarking because some plants are taller than that, a lot of plants are shorter than that, so it kind of gives you something in the middle. Like the tomatoes, it's common to be having them growing up to 8 foot high. Okay, so that's the sensor layout. We're going to step back and just talk about what our outdoor weather did a little bit last year, because everything's kind of tailored around a response to the weather. So all the graphs I'll be sharing with weather data will go from November 1st of 2023 to November of 2024 here. So we go through the winter time, and then we have our peak of summer. We had some nice cold weather. This seems a little bit like deja vu. We just had weather like this in the last couple of weeks here. Actually, it didn't quite get as cold this year. These are measured temperatures, not wind chill, which is a little bit of cheating if you want to use wind chill. But we had a record or a recorded low of negative 21 Fahrenheit here. And the dotted line is our average for the day, with the blue and the red are our highs and our lows. And then I have the dotted line here is at 32 Fahrenheit, which is kind of its freezing point, and kind of a nice benchmark to compare and read the graph. So what did we have for growing period last year? This is outside. If you're growing outside, we had our last frost on April 25th. So if you were lucky and you had all your plants ready to go, you could have gotten them in the ground shortly after that if they're frost sensitive. And we had our first frost where the air temperature got down to 32 degrees on October 4th, which is actually a really long growing season for us for outdoor. I would say on average, it's usually we have frost a week or maybe 2 weeks before that, really. So we had a longer than normal, nice frost-free growing season. And something to note is actually in my outdoor growing, which is a photo of it up here. We had our first frost damage on October 1st for pepper plants. And the recorded temperature was 38 degrees Fahrenheit outside. So that's kind of interesting. So it didn't get down to 32, but it froze. Why might that be? And so hopefully I don't put people to sleep, but I'll talk a little bit about the physics of what happens when growing outside, because that's important to understand when you move into growing in a high tunnel. So how could it freeze if it only got down to 38? We are in a little bit of a low area, so our air temperature is, maybe a couple degrees below 38, but still nowhere close to 32. So talk about the way heat moves. In this system, there's really two ways that heat is moving. So first of all, we've got convection. Heat transfer occurs through convection, through cool airs moving over the plants, cooling them down, and it can only cool them down to what the air temperature is. So it might be able to cool the plants down to 38 if it's 38 degrees outside. And we have some convection from the wind happening. We have convection with the ground, which actually gives a little bit more warmth the closer to the ground you get, because the ground is still warm in the spring. But we've got something else going on too. We've got heat transfer through radiation. Thermal radiation, it moves heat from the leaves to the cold sky. And the rate of that heat transfer depends on the leaf temperature and the sky temperature. And on this day when it got down to 38, we had clear skies at night. And so the sky temperature was quite cold. I'll have some pictures with the thermal camera later on that you can see, but it's common for the sky temperature to be negative 30, negative 40 degrees. And so you can have a good amount of heat transfer to that sky because you have a direct line of sight from the plant's leaves to the sky. So these are pepper plants. Their leaves are pretty thin, and they take frost damage very easily. It's very easy for them to cool down to below the air temperature due to radiant heat loss to the sky. All right, so we'll talk about the high tunnel and how that performed. We've got kind of a few more lines on this graph. So we'll kind of talk through this a little bit. We've got the same blue and dotted line and red line for our ambient weather conditions. And then we have the daily high and low in the high tunnel recorded here. So the red line is our high temperature that was recorded each day. And the black line here, which is probably the one of most interest, is what the low temperature was in the high tunnel. And you can see kind of a lot of interesting things with this. On that night, or on these nights back here, when it was getting down to negative 20-ish at night, we saw some temperatures down to negative 10 in the high tunnel. So it kept it warmer than outside that night by 10 degrees. But if you look at a few other nights, there's a lot of nights that pretty much ended up matching the air temperature we had outside, especially in the early part of the season. When the ground in the high tunnel is cool, it'll pretty much meet that outside. And if you can look at the end of the growing season, the high tunnel does stay above the outside temperature at night better than in the spring. And that's because the ground is warm from the summertime in the high tunnel, and you get some heat transfer off the ground that keeps it a little bit warmer. And you can kind of see here are some of the lows that we had in the high tunnel, 33, 31. So we're really flirting with freezing air temperatures there. So what we ended up having in the high tunnel here is 190 frost-free days. That's nice. That's 28 days longer than growing outside. And then this here's where I'd step back to that heat transfer stuff I talked about. The radiant heat transfer off of leaves in the high tunnel actually is way less than it is outdoors, because you don't have a direct line of sight to the sky. The radiant heat transfer from the leaves to the glazing surface is much lower, because the glazing surface is much warmer than, you know, -30, -40, like the sky temperatures might be. And so what I've observed is that you can see freezing temperatures, measured air temperatures in the high tunnel, but you won't actually take frost damage until you actually get below 32 Fahrenheit for air temperature in the high tunnel. So of course, when you have plant damage, depends a lot on the plant and what you're growing, but that's one of the ways the high tunnel gives you an extended growing season, by reducing the amount of radiant heat transfer. So the last graph was the whole year. Let's look at just 1 day and what's going on in the high tunnel. This here is February 7th. So you're probably not growing plants yet, but you might be wanting to grow plants. We have the dotted line again is 32 Fahrenheit for reference. And on February 7th, 2023, this gray line here represented what our outdoor temperatures were. And this was actually a really nice day. We got up to 37, a high of 37 on February 7th, which is pretty nice typically for us. But the high tunnel temperature, we actually were below the air temperature for a little bit at night. And then when the sun came up, our temperatures shoot upwards. And we had actually a difference from inside to outside of 56 degrees Fahrenheit. It got up to 93 inside. So if you had ventilation systems, you know, you'd probably want those to start kicking on at those temperatures if you were growing things at that time of the year. I kind of talked about these. The soils keeps it cool at night. It heats up really fast, cools down really fast. And this kind of highlights some of the big areas for improvement in the high tunnel design. First of all, if we could reduce the heat loss, we could reduce how fast it drops and cools off at night. And it would also be good if we would not get quite so hot, because this puts plants through a pretty stressful shock if they're going from really cool nighttime temps to real high daytime temps. So if we kind of step back to our full year thing, we can see how warm it's getting in our high tunnel here. It's heating up nice, actually a bit uncomfortably nice. And so what could we do? How could we store some of that heat and make it so it doesn't go up and down so fast and so radically? And then our nighttime temperatures, they're barely getting above the outdoor temps. So these are kind of some of our big areas for improvement to improve our growing season in the high tunnel. What could we do to make a better high tunnel? What if we set ourselves a goal? What if we tried to stay above freezing for as long as we have enough daylight to grow? As we know, this time of year, it's been pretty dark. We don't really have enough light to have active plant growth for a period of time. And so what is that? So generally, there's kind of this rule of thumb that, of course, it's not true for every type of plant you might want to grow, but for a lot of plants, if you have 10 hours of daylight, then most plants will have enough light to actively grow and produce fruit or whatever vegetables you're growing. So if we look at that, we have a growing period in South Dakota here where we have more than 10 hours of daylight from February 4th up to November 6th. Kind of exciting because we're getting close to February 4th. Maybe that's why we all want to start growing things now. This period of time where we have less than 10 hours of daylight is often referred to as the Persephone period, which was kind of coined by Eliot Coleman in the Four Season Gardener series of books and stuff that he has published is where that name comes from. So what could we do? Could we get our high tunnel to be productive throughout this whole time frame? If we could, that gives us 276 days, which is 114 days more than what we had growing outside. And that'd be pretty impactful. I'm going to talk a little bit about one of the example greenhouses that is a good inspiration for what we could do and many of these things. So if you have follow greenhouse stuff, these Chinese solar greenhouses is a pretty common growing structure. These are developed in China, which comes from the name there, but China actually has the highest greenhouse-based vegetable production in the world. This here comes from a paper published in 2010. At that time, they already had 1.9 million acres under production in solar greenhouses, which is 17% of their total. And that's kind of mind-boggling, the number of acres that are growing fruits and vegetables in a structure like this. But these are nice examples because they are a fully passive structure where they're not putting any external heat in to grow. And so just to kind of give a scale of what the quantity of these out there is, I thought I'd share this little video from Google Earth where we go in. This is Shenyang here in northern China. It's outside the city here. You can zoom in and look at all of these structures here. These are all solar greenhouses. Just the quantity of them is kind of mind-boggling, and the amount of produce they're producing there is substantial. So what if we took some of that information and tried to apply this to a high tunnel? Maybe it's important to step back. A high tunnel is different from a greenhouse. The USDA defines a high tunnel as a temporary structure. So when we're designing or building a high tunnel, we want to keep that in mind. It also doesn't have many energy sources. External, maybe electricity may or may not be available, or it may be available but minimally. And the high tunnel should be temporary, such that you could remove it without having concrete foundations and things like that. So what we want to look at when we are doing this, we want to, we have this kind of tough paradigm that we're working with. Low cost, we have to have low cost transparent materials, but they all have poor insulation properties. So we want to balance maximizing the amount of sunlight we can get into the growing area, but yet minimize the amount of heat loss that we have and insulate surfaces where we don't get enough sunlight through them, or don't get enough sunlight for it to make sense. So if we look at our traditional high tunnel up here in South Dakota, our sun kind of has rotates through several different sun angles throughout the year. In the summertime, at noon, we have our sun is at a 70-degree angle above the horizon. You kind of see our whole plant beds easily illuminated. And in winter, our sun is low in the horizon to the south at a 22-degree angle. And kind of see how it goes. And we're not actually getting direct sunlight through a lot of these surfaces in the wintertime. So that's kind of where optimizing the structure to fit our growing environment and our seasons can give us some benefits. So if we take this and like the Chinese solar greenhouse, we have an opaque insulated surface on the north wall and roof, and design the angles of this so that we get full illumination of our growing bed in the winter time, and of course in the summertime, because we don't want to shade out some of our plants, and we want to use all the light energy that we can get for growing stuff. So this kind of sets up the starting point for this, and gives us, there's a bunch of papers talking about optimization of this, and how to give, what is the optimal angles and percentage of the surface to be insulated and stuff. And so I use that. There's actually hundreds of papers on these topics, but some of these that were had calculations that we could extrapolate to our exact latitude and longitude. And so here's kind of a side view of the structure that we built. One of the problems with the high tunnel was it gets so hot during the daytime, and then it just has to dump all that heat outside. So the reason it gets so hot so fast is because the heat storage capacity or density of air is pretty low. So air can only hold 0.018 BTU per cubic foot per degree Fahrenheit, which is why it heats up fast and cools off fast. On the north wall here, we used concrete, but these are portable concrete blocks, and concrete has a heat storage density of 32, which is a bunch more than air, clearly, but it's not as high as other things, like if you had water or something, but it's still orders of magnitude way above air. So we have that on the north wall. And then if we look at our sun angle in the wintertime, the shape and geometry of the structure is such that it fully illuminates the blocks through the 3 months of the winter surrounding winter solstice in December. And then in the summertime, it is set up so that the blocks are actually shaded for the 3 months around the summer solstice, so that the blocks do not get direct heat, because you don't really need to be heating up your growing area more than you need to at night, because it can get pretty warm. So that was the plan for the structure. Here's an image of what we ended up building. We used these large mega blocks, or they're 2 foot by 6 foot concrete blocks. These were built locally here in Brookings. A lot of cement plants make these now. These are made with waste concrete. They have, after pouring sidewalks or driveways, they have some extra concrete that they mixed, and when they come back, they, instead of throwing that away, they can pour it into some molds, and they make these blocks. And so those blocks are pretty cheap, and they have a handle on top so that you can lift them and move them around. And so that fits with the portable strategy between with the high tunnel. The frame structure is all standard 2-inch piping, that steel piping that's used for greenhouses and high tunnels, with the kind of the standard couplings and fittings that you would see for a high tunnel. So yeah, so that's kind of what the frame looks like. Turned out pretty good. One thing I did, I was mounted this into the frame into the top of the concrete blocks. Definitely in the future, I do not recommend that, because it is horrible to drill holes into concrete block. And because this concrete is waste concrete, from different types of construction, from highways to driveways to foundations. A lot of the blocks are very different types of materials, and some of them have like a red Sioux quartzite aggregate in them, which is nearly impossible to drill through. So definitely in the future run the frame down to the ground with the same kind of stance as the other parts of the structure. Something that's in the image you'll see is all these black pipes. These are for a future or current part of the study that is happening with the climate battery using the ground below the structure for heat storage. So for the data I'm sharing tonight, these are all cut off and weren't used for the period of time that we're talking about, but they'll be part of a future information that I'll be sharing. So now, how do we make an insulated wall and roof? And this is interesting because I really didn't come across any good examples of people doing this, especially in a portable temporary method, which is what the high tunnel is kind of trying to achieve. So it worked out pretty good, but there's definitely some things not to do. You kind of see here it's a tarp. The outside tarp is vinyl, which is UV resistant. Of course, it costs more, but you kind of need that because it's getting sunlight out here, and it's going to break down pretty fast if you use a regular low-cost polyethylene tarp that you might buy at Runnings or your local hardware store. Vinyl is what's used in the larger hoop buildings that we see nowadays that are popular for for livestock or parking machinery, and it's a same material with the same kind of durability characteristics. And then on the inside is a standard polyethylene internal tarp. I want to use that because it's lower cost and shouldn't be getting as much direct UV light, so it should hold up okay on the inside. And I ended up using 1-inch expanded polystyrene foam board in between. I initially wanted to use mineral wool because it has a higher R value and it has good moisture resistance. But the problem I ran into was it's not rigid enough, and so it was sag. And you can see here, you can see it's sagged down, and then you kind of just stuffing it in there. It really doesn't give you a good consistent surface to work with. So definitely recommend using a foam board or some rigid material. Mineral wool is more rigid than fiberglass insulation, but it wasn't rigid enough to maintain its shape and height in there. So then the glazing surface is a traditional inflated polyethylene film that you'd use for most high tunnels across the top surface. Not sure if these are kind of new things, if anyone has questions about inflated polyethylene film, or if those are kind of things you guys are familiar with. I wasn't really planning to talk to the main glazing a whole lot. Talk a little bit about the roll-up vents here. This is something I thought would be easier. I just figured this stuff was well established. Everybody had nice inflated roll-up vents. But when I came into this, found that there's really not a lot of great information out there, and not a lot of people are doing this, or at least not maybe doing it super well. So do you want to inflate or not? Is it worth it? Because it's going to take a little bit extra effort. So non-inflated polyethylene film has an R value of 0.85. This is insulation resistance, and it's used to characterize how much heat loss you have through the film. So 0.85, that's pretty low. Building house walls, they might have R values in the 20s nowadays. Ceilings in your house, they would be 30 plus. So 0.85 is low, but kind of have to expect that because of this thin film. And some of the drawbacks with the roll-up fence and single layer, it's really tough to minimize flapping and eventually from the wind tearing of the film. And there's a lot of strategies people use. You kind of see these ropes on here. You pull those tight to hold it so it doesn't flap as much, but it still will because you can only keep it so tight. And then another thing is usually people are going just for kind of some minor season extension, not seeing how they can do all year. And you end up getting, because this rolls up from the bottom up, it is set up so there's this panel right here is overlapping. So there's a fixed layer of film and then the roll up goes over it. But when this can flap around in the wind, I noticed you can get cold air infiltration just right through that pretty directly. And that's probably really where a lot of your heat losses is happening, more so even than just being conducted through the film. So to inflate the vent, so this is what I did. It's kind of interesting. There's really one supplier I found that has some materials for doing this, advancing alternatives, and they have a few nice videos of how to install this, and they can provide you with some of the materials, but it's pretty simple. You have a separate inflation fan. So in the main part of your structure, you have a fan inflating it. You have a secondary one in the vent. Mine's installed like right over there. And then you have a jumper between the vent, which is 2 layers of film, to this panel here, which is a fixed panel, and that's inflated as well. And so what happens when you are rolling down your vent, both sides of that inflate and they press against each other and give you a much better seal on that end panel. And then they sell a special aluminum extrusion piece that the pipe here rolls down, rolls over, and then it rolls back up that pipe. And so it kind of locks and seals, whereas traditional roll down sides will just roll down and maybe you just hit a flat stop or a board, and you'll get a lot of air just blowing right in that if you don't have the roll lock or something for that to roll around. So with a double inflated, or with an inflated double layer of film, you can get an R value up to 1.25. So what does that mean? If you were trying to heat your structure with propane, for example, to maintain 45 degrees at night, and at $1.65 per gallon propane cost, you'd save $140 of propane per year. To just give you kind of a rough feel of what inflating or not inflating just the vent would do. That's just heat loss through the film, not through the end walls. So, and another big thing I didn't talk about is this is really nice and solid in the wind. So you don't have any flapping. It's pretty nice how tight that is, actually, because it's got its own dedicated fan to fill that vent. So it's really good in the wind.
It also repels hail a little bit.
Yes, out west, you guys have a lot of hail, so makes it, yeah, probably a little bouncy. I didn't have any hail to to test on that, but yeah, I believe that. I got a few thermal camera images here. If you haven't looked at thermal images, these are a little bit hard to read at first. So we have some false coloring, which tells us approximately the surface temperature of stuff. And so I'm sorry, I realized after I made these here that I have my units aren't the same, and I've got Celsius and Fahrenheit. So ignore the numbers exactly if you're not comfortable with Celsius. But the main takeaway you can see with these So in the non-inflated side, you can see the roof is cool. Or actually, you can't directly measure the polyethylene film temperature with infrared cameras because it's very reflective. But you can see the general trend where we're cooler right above the vent, and then it's warmer right below. And it's warmer because we're seeing that heat conduct out of that uninflated vent. And so we can see our heat loss visibly there. And then when we have it inflated, we see nice consistent temperature across that vent where we're getting a similar insulation level on our vent as we are on the main part of the structure. Maybe something cool to note too on these images, you can see, I'll stick with the Fahrenheit one. So blue is colder, and this is actually, the blue up here is actually reflecting infrared off the sky. We can see our sky temperatures, they're dark. So it's actually minus 40 Fahrenheit sky temperature. So when you're calculating your radiant heat loss from your leaves, it's that temperature of the sky that dictates the amount of heat loss your plants see. And so when you have your glazing material here is a balmy 21 or 30 degree Fahrenheit, you actually have way less radiant heat loss. And so you aren't going to freeze as fast. But I think it's cool in the images where you can see that. Then we're going to talk about concrete blocks. Do we have any questions we should talk about yet, Rhoda?
Yeah, as long as you're talking about concrete blocks. There was a question about whether the Chinese use concrete blocks or do they use water containers or?
Yeah, that's a good question. The Chinese solar greenhouse, because the greenhouse, it's considered a permanent structure. They have tested and use a multitude of materials. The older original designs, and probably some still use actually earth, compacted earth. So they'll make a form and put soil in it and compact it and use that, usually with a thin steel form to hold it in place. Probably the more common method is concrete blocks. It's not the same concrete materials as what we have, and they're usually mortared together so that it's a permanent wall, not as temporary, and they're not as thick as these. And then they'll either berm soil up on the outside of that wall for the insulation, or use insulation on the outside of it to retain the heat in the blocks. As for water, I haven't ever seen them using water in the wall itself. There has been some experimentation with heat exchangers on that wall surface. Like if you have the solar water heaters with those tubes, basically an array of tubes on there that will heat water and give you more heat storage than just concrete or packed earth. But that adds a lot of complexity and cost, and may not be worth that invested extra cost. So this is just a thermal picture from when we were building it. I think after the sun went down and I was packing stuff up for the night, I was like, oh, let's take a picture. And you can kind of see, this is the FLIR camera does a photo overlay with the infrared overlay. So things don't line up perfect, but it helps you to tell what it is you're looking at. You can see how the blocks are nice glowing red warm. So for the concrete block part of the study, I started off with all the blocks being natural colored. It takes extra time and money to make them black. So I thought, oh, maybe it's nice if I don't have to do that. Let's measure it and see how big of a difference this has. So I put in probes into the blocks, 2 probes into each block, one 1 inch deep and one 8 inch deep probe in each. I wanted to do them deeper, but my drill bits said otherwise. So we were stuck with 8 inches, which is still 1/3 of the way into the block. And then I stained one block black for comparison's sake. So and we ran these measurements from January 4th to middle of February here. I think it's February 18th. And this here is a graph comparing the temperature difference between the black to the natural colored block. So this is the temperature difference, how much warmer the black one was than the white one. So of course, at a 1-inch depth, you see on these sunny days, we get these nice spikes of the blocks heating up. And of course, at 1-inch depth, it heats up faster than at 8 inches. And so I was surprised. Actually, I wasn't sure that it would be this big of a difference because I didn't know the exact emissivity or the radiation absorption rate of the natural concrete. So I thought this was pretty positive. We got up to a little over 9 degree of temperature rise in the black block versus the white one. And this is still in January and February when our day lengths are shortened. So that was pretty substantial. Maybe for reference, about 75,000 BTU more heat is absorbed in the outer 8 inches of block than in the natural colored block, which would equate to, for reference, a gallon of protein is 92,000 BTU. So a little under a gallon of propane difference here between the black and the white blocks. And thermal image is kind of cool too, where you can see our black block is warmer than our other non-painted blocks. So after that, I decided, hey, we should probably make all these blocks black because that's worth it. So I dyed them all black with concrete stain. Looking at the overall temperatures of the blocks through that time period here. This is just a black block, and you can see the nice cycles day to day. And we'll see in one sunny day, we'll see at 1 inches deep, we'll see 31 degrees temperature rise actually in that block. And then at the 8-inch depth, because it takes time for that heat to penetrate, we only get up to 12, but that's substantial. That ends up being in these kind of strings of days here. The block wall, the structure is 60 foot long. So we had approximately 225,000 BTU of heat being absorbed each day on those sunny days. In just the outer 8 inches of block, there's some additional heat deeper in, but I didn't have great data on what that was. So several gallons of propane being absorbed every day. So how did it do? So this graph here is laid out similar to the one that I shared for the traditional high tunnel, but I have the kind of our target dates on here as well. So again, the red line here is our daily high temperatures. The black line is our daily low temperatures that we had. And then our dotted line in the blue and red here is our outside temperatures. So you can see we're staying well above these low temperatures we saw outside. If we go by 32 Fahrenheit as our freezing temp, we have more than 247 frost-free days. Towards the end of this here, I did have the climate battery going because we're getting into this next winter and I need to start collecting data on that. So when exactly we would have had frost here without it, I don't know, but really excited for our early season, which is actually the harder part of the year to prevent freezing on. We actually were frost free from February 28th onward, which is really early. So over the regular high tunnel, that gives us an increase of more than 85 days of growing season frost free. And you can I could put maybe the numbers on here. But remember in this cold spell that we had in January, our regular high tunnel stayed about 10 degrees warmer. It got down to -10, whereas here we're still positive. This actually was the lowest recorded temperature throughout this period of time, which I measured +15 right here, which is exciting because there's a lot of plants you could overwinter in a subtropical climate that would handle that no problem. So there's a lot of opportunity for growing overwintering plants that you couldn't overwinter outside or in a traditional high tunnel. So just an overview comparison here of the three different sets. The outdoor, we had 162 frost-free days. The standard high tunnel is at 190 frost-free days, and this extended season high tunnel had 276 frost-free days. And I thought maybe it'd be nice to ask the audience a question, or you could send an email to me afterwards. But I'm looking for like what other metrics would be nice to compare high tunnel performance than just the frost-free growing days. What are some things that you guys would find of interest, and could put that in some future webinars or recordings. And I can also use that for as we go into the climate battery, storing the heat in the ground below the structure analysis to compare these different things.
Shannon, have you measured any of the light level with your design?
Yeah, that's a great question. I hadn't originally planned to do that because the light level should be the same as a traditional high tunnel, but I really didn't find a lot of data on that either. So I did start recording that here this last winter. I think starting in November, we'll have the light levels recorded, and then can calculate the DLI, the daily light integral. And I think that'd be nice too, to kind of refine, and then we could set up like, oh, these are the plants that get enough light during this period of the year. So, if you could keep it warm enough, give them both the temperatures they need and the light they need, they can be productive. So yeah, that's a good one that I started tracking here after this. Mm-hmm. I thought one more fun thing I kind of share is just a snapshot of what grew in here in 2024. I wasn't necessarily planning to do a lot of growing, but then I thought, oh, I probably should, because that's an important part of the data, because nobody's going to be running these without growing stuff in them, which maybe is more common than I thought. But so I use peppers. Partially, I had some customers that were interested in that, but also peppers are great temperature sensors because when they freeze, they make it very obvious, and they're very sensitive to that. So I mostly grew peppers across the whole structure so that I could see when it froze. But anyway, I was a little behind. Wasn't really expecting to be able to start planting stuff at the end of February, being frost-free at that time. But I had the plants in the ground and stuff here April 21st. which is still a month earlier than one would normally do that outside. So by June, they're looking nice. This row here that I have in most of the pictures is a Capsicum chinense species. These are the super hots. Specifically, this is Trinidad Moruga scorpion. So they're known to be pretty hot. I think maybe in 2010s, it was the hottest pepper in the world. They've been superseded a couple times now. But by June 24th, they're looking pretty tall. But by July 20th, I got my wife for scale here. We're definitely knee high by the 4th of July. In fact, I think we're getting shoulder high by the end of July. And so I wasn't maybe prepared for the level of growth that I was going to have. I didn't have trellising tall enough for these by August 17th. There is as tall as Chris here. Chris helped with a lot of the CAD modeling and work on the structure. He stopped by to inspect peppers too. By September, it was getting way out of hand. They're getting pretty darn tall. And here in December 5th is really when I started to see them the first frost damage on the plants. By this time, the climate battery is running again, so this isn't just the blocks giving us this level of extension, but I think the blocks get us pretty close. And it was wild because I wasn't prepared for that level of growth. Anyway, so yeah, so if you're interested in the tour, if you're from South Dakota, send me an email. Definitely love to give tours and show people around and check out the structure. You can email me their first name, last name at gmail.com or find contact info on the webpage. And of course, you can follow us on Facebook and Instagram if you want pictures of random things growing and snippets of data every now and then. And of course, special thanks to South Dakota Specialty Crop Block Grant Program for making this research possible and helping other growers. So what else do we have for questions, Rhoda?
We have a number, actually. There's questions about, is there something that you could have tried besides concrete? And I think you talked a little about that, but maybe a bit more.
Yeah. Well, I think there's definitely other possibilities. The challenging part, can be sticking with something that's portable to meet the high tunnel requirement. These blocks are portable, but other things that you've probably seen people sharing, talking about using water barrels or something like that. Water, of course, has more heat storage capacity, but it's also very heavy, and it's even heavier than concrete. So if you do want to stack barrels, I would just have warnings of be safe. And you really, the amount of weight that water has, you probably need to pour concrete to safely set them on something and not see uncontrollable settling that might be an issue there. Other options, I don't know. Definitely packed earth is an option that people can do, but you got to make it solid, and so there's complexity to that. But those would probably be the two main things that you see people doing as alternatives.
How did you prepare the ground for putting the concrete blocks on top?
Yeah. You pack it as well as you can. Because I dug and excavated everything 4 foot down for the climate battery, I tried to not excavate where I was putting the blocks so that the ground would still be as naturally compacted as it is. But even that isn't probably really enough. I used my tractor with the concrete block in the bucket and drove over the area back and forth. to get it as compacted as possible. There's still you can see settling with the blocks if you do that. It's not really settling, but you will see frost causing the blocks to shift. So if you do want to use the concrete blocks, you should bury the first layer of block at least halfway, so that it's more stable. And compacted on both sides. So is what happens in the spring. Well, and through the winter, inside your high tunnel, the ground does not freeze, and the ground outside your high tunnel does freeze. And so when the ground freezes, it expands, and so the ground outside your high tunnel is rising up, and the ground inside is not. And so, maybe you'd see a little bit of a tilting forward, but then when what really happens is in the spring, when your ground outside thaws, it's going to shrink and move a bunch. And so that's why you want to put the blocks in the ground a little bit to get them stable.
I was thinking about our expanding clay out here in the west part of the state, wondering how that might do.
Yep.
Along those lines, there's a question about whether the blocks would help the structural integrity.
Yeah, well, a well-designed high tunnel frame shouldn't have structural issues, but there's a lot of them that aren't. So I would say it depends. If you have a good built frame, it's going to withstand the wind and the snow load that it was designed for. A lot of them aren't really engineered, so they're not going through the calculations and making sure that it is strong enough. I didn't put any of that calculation analysis stuff in the presentation to keep it short enough to fit in our time frame here. But the frame strength is, I designed it for North Dakota snow loads. And then the other thing with the high tone frames is a lot of people, even like the example I showed with the tomatoes, people will want to trellis their plants from that frame structure pretty frequently. And so they need to be strong enough to hold both the snow and the wind and the weight of all your tomatoes that are hanging on it, which can be, maybe the tomatoes are heavier than all of those other things put together, possibly. Trevor reinforces or supports some of that by having some vertical wood posts along the length of his tomato rows to help with the weight load there. So our next questions.
Can you see those? How much water did the peppers use? And have you thought about rainwater collection?
Yeah, the name of our farm is Wayward Springs because we have natural spring water. So we have an infinite water source there. And to my high tunnel, it's actually gravity fed because the springs are in the hills above it. I would say sometimes it's more of an issue for us with too much water around than too little. But it was pretty dry this year. I have drip irrigation lines. I think maybe it's maybe one of our presentations for the conference here is about drip irrigation, but I run drip lines to each of the plants, and it's below the plastic mulch. And I found that I didn't need to water very much, really. Every couple of weeks really was all I needed. I probably don't have a timer on it, so I probably let it run too long when I did run it, but yeah, it worked out well.
There's a question about, have you kept track of the costs involved with building the high tunnel this way versus a traditional?
Yeah, yep, I do have all that information. I didn't have that compiled in here. The frame structure is made with the same type pipe and hardware and stuff that standard high tunnels are. So the frame is similar to another one of the same square footage. The concrete blocks are very cost effective, I would say, for their size and weight. Locally here, for the 6-foot blocks, they were $50 a block. So I don't know off the top of my head, and I didn't put together the cost info for the presentation here. But it ended up being like $2,500 or something worth of block. And I got them from our local cement plant here, which is 8 miles away. I would say they're very heavy. So I'm not sure how many growers have the equipment to move them. They're about 4,000 pounds a piece. And my tractor's the Ford 9030 bidirectional, so it's kind of like a small payloader, can lift them barely. But the articulating loader, lets you position them quite precisely when you put them down. So that's really nice. So if you're looking for someone to do that, someone with an articulating tractor versus standard loader tractor is nice.
I have a question. I'm not sure I'm following. What manufacturer for the Chinese high tunnel can fabricate the top? I would like to use berm soil over the north wall and can build the remainder. The manufacturers I've gotten in touch with thus far have told me they don't make parts.
Yeah, so if you wanted to purchase a Chinese solar greenhouse from China, there's lots of manufacturers of them. There's probably a variety of things that kind of make them a little bit hard for a lot of farmers. So high tunnel kits are sold as kits that you can put together with regular hardware like bolts. Most high tunnel kits that you would get from China, all of those pieces of frame are welded on site together. So you'd have to have the welding skills and those fabrication skills typically if you were to order them. I don't know if that answers the question exactly. There's many manufacturers, and I can't pronounce their names.
Well, if you have further questions, I guess you can email Shannon. And by the way, I think we misspelled your name on our publicity for this talk. We apologize for that.
Yeah, use the email that's on the screen for anyone.
There's a question if you could use dense pack cellulose or other material in the space for the insulated tarp of the north wall if the tarps were drawn very tight. And also, how were the tarps attached to the frame?
Oh, yeah. How are the tarps attached is a really good question, because I don't know. I probably thought too hard about that for too long. And I ended up just using the same wiggle wire channels that hold on the polyethylene film. I did some test fitting of a couple different thicknesses of tarp to make sure that they fit. And so both the inner and the outer layer just go right into that regular spring wire, wiggle wire channel that high tunnels typically use. And it held nice. Was there another question mixed in there? Other materials for insulation? Yeah, there's probably a million things you could consider using. I would say foam board is great because it's rigid and stays where you put it. If you got stuff tight enough and you had a way to put it in there, you could do cellulose, all kinds of different things. But you'd want to think about how long those materials last and whether or not they would get damaged by humidity or condensation occurring in there.
Yeah, I was wondering about that with cellulose.
Yeah, I wanted to use the mineral wool because mineral wool is basically like a heated, expanded rock, right? So it's not going to be very is not damaged by moisture much, but wasn't rigid enough.
We have several questions about the climate battery. I think people are intrigued by that. Um, can you share any preliminary data on the climate battery? Uh,
Um, I don't know that
Tubing lengths,
yeah, I don't think I can
depth,
share
etc.
data, but I can talk about what the study is entailing. So the intake for the tubes is along the wall at the base of the block, the north wall, where it typically would be, and they run the short length of the high tunnel. Uh, the high tunnel is 25. The growing area is 25 foot by 60 foot. To the outside of the block is 27. So the length of the pipe is that 25 horizontal plus the height to come up out of the ground. For the climate battery study, if you followed some of the previous work I did on the greenhouse several years ago, I used the manifold system and found that the Z style manifold restricted the range of airflow that I could push through the pipes to get the full range of performance data that I wanted. And so to overcome that challenge, I ran every single heat exchanger tube is separate with no manifold and has their own individual fans on them so that I can control the fan speed through the pipes individually for the purpose of the study and collect a wider range of airflow rates that aren't possible with a manifold. I'm not going to say at this time that I would recommend somebody building it that way because it requires you to have a lot of fans. I think I've got like 85 fans, and putting all together and wiring all of those is a little bit cumbersome. Something probably everybody's up to. Or at least I'm not sure if I was, but I did it anyway.
There have been some systems that use water instead of air running underneath. Did you look at any of those, and did you have any comments on that?
Yeah. Those are nice. They are a little more complex, and so I don't know if you could necessarily call it a high tunnel with that complexity, but you have to have an air to water heat exchanger system. Then your water flows through the ground, the water to soil heat exchanger, and you have a few more heat transfer phases that you're working through, and just adds more equipment and complexity to it. But I think those are more common in large scale commercial type structures where they can pay for that large infrastructure that takes.
Someone commented that they build a greenhouse within the greenhouse, basically a covered plastic bed, uh, which will retain heat for quite a while.
Yeah, and well, that's maybe a bit of a growing trend in the Chinese solar greenhouse for even more northern climates. So I didn't maybe point it out too much in the images of the Chinese solar greenhouse, but they'll often have a roll-up blanket. I can see if this will take me back to that slide. So they'll have a roll-up blanket that goes down over the top of the structure at night. And so that allows you to have a very high insulation level covering over your glazing film at night when you really need it the most. The challenge with that, there's been, so here you can see the roll
Mm.
of blanket that would roll down over that. The challenge with that in northern climates is we'll get snowfall when the blanket's down at night sometimes, and then that would be a barrier to being able to roll it up in the morning. And I'd probe some of these manufacturers over and over again. Like, okay, well, what do you do? What's the normal thing that that folks do? And of course, a lot of the regions that these are used, the snow would melt, and they just don't open it until the snow has melted off. But maybe because I kept probing, they eventually just sent me a video of a guy up there shoveling snow off. It's like, oh, I see. You just manually move the snow off the top. It's like, oh, that's probably not something that's going to work around the United States that well for safety and many other reasons. Um, so, but to deal with that, well, and maybe I should say the other thing is if moisture gets into that blanket, the blanket will freeze. I saw a nice study in Manitoba where they were testing the blankets, and that's what did end up happening is they got some moisture penetrated into the blanket, and then the blanket froze solid, and they were done for the winter because they couldn't open it. So people have built a secondary frame structure basically over top of the primary greenhouse to protect it from snowfall, which seems to work, but you're almost doubling your frame cost having to do that, and another layer of film and reducing your light level through some layers of film. And but it's an option, and there's a few folks that can provide that from China. I'm not aware of anyone in the U.S. making something like that, but
If there's a way to do it, somebody's tried it, right?
yeah.
There's a question on what it typically costs you to heat your extended season tunnel. And I don't know if you've heated it yet.
Yeah, I haven't put any heating energy into it, so zero.
That was an easy one.
I like easy questions. Yeah.
Uh, any benefit to combining the thermal mass of the back wall with the thermal mass of the earth?
Yeah, that's probably a good question. I I would like a way to turn the blocks off so that I could test just the climate batteries separately. But to make it cost effective and fit within the grant program, I have everything kind of lumped together, and I can't turn off the blocks. I could turn off or not hook up the fans, right? So that's why the order of the study is do the block testing first and then do the fan testing. But kind of debated like, what if I cover the blocks with a sheet or something for the winter? But I did not do that.
Well, there's a similar question. Did you do any calculations on just the blocks without the insulation?
Oh, I think you would lose a lot of heat. There's there's a lot of good data on that from the Chinese solar greenhouse research, and what they have kind of defined for their climate, what the best insulation level is, and actually the 1 inch foam board that I have is probably really too thin. There'd actually be quite a bit of benefit to having a thicker insulation layer on the back of that, so you don't lose as much of the block's heat out. Maybe when I'm done with this project and want to take stuff apart and reconfigure it, it would be good to at least get up to a 2 inch or more on that, and the blocks would actually perform much better then because they wouldn't be losing as much to the outside.
Just a few questions left. One is, and I maybe can answer that myself, is what hardiness zone would be equivalent to that number of frost-free days? Hardiness zones are actually minimum low temperature average minimum low temperature. So I guess if your lowest temperature in the tunnel was what,
15?
15, you'd probably be what, already know, some 5 or 6 maybe.
Yes, we're zone 4 and we're negative 25.
Yeah.
I think we get to zone 6 or 7. I'd have to go look it up.
At any rate, it's based on the temperature, not the number of frost-free days.
Yeah, yeah, yeah. So if you're growing perennials, the growing zone metric is okay. For
And
annuals, it's the growing length season.
I'll end with this one, other than just want to thank you. This was very interesting. 15 Fahrenheit
Thanks,
would be on
Tim.
the border
Thanks,
between
Tim.
8A and 8B, I guess.
Yeah. Yeah.
Um,
So
this
that's
method,
fig worthy, right, Tim? We can grow figs now.
right?
I didn't have a picture. I did have a fig plant that I just put out there for last winter, and it overwintered fine. So figs are a subtropical that are fairly cold hardy, really.
And then we have the comment, this method seems so much more efficient than the typical high tunnels we have used. Why has this not caught on more in the US? Enough people haven't watched your seminars, right?
Maybe that's it. Yeah, I don't know. That's a great question. I'm not sure that I know the answer. I think maybe why have high tunnels caught on um, at all? And maybe some of the answer sits in that, as the EQIP program does cost sharing to growers, so it makes them more affordable and encourages it. Um, and
That certainly has contributed.
yeah, and I mean, there's a lot of great reasons for high tunnels other than season extension. I think that's what I've mostly talked about. But there's tons of benefits to the quality of the produce as well. That could be a whole nother topic.
We're going to have to book you for a few years here. Well, I think that's everything. Thank you to Shannon, and thank you to the audience for your engagement, for your good questions and discussion. Reminder, before you go, will you please open the survey link in the chat and share your feedback on tonight's session? We always use these to improve future programming. And put my video back on here. We look forward to seeing you again on Thursday for our last session, which will highlight SDSU research updates shared by Jocelyn and Christina of the SDSU Southeast Research Farm and our SDSU Master's Graduate Research Program. And as always, remember that each of these sessions are being recorded and you can share them with others. You can go back and look for that detail that you forgot about, and all on the YouTube channel for SDSU Extension. And thank you again for completing the survey, and thank you so much, Shannon, for sharing your knowledge tonight.
You're welcome.